After knowing the functionality of the code, we go on with the demonstration part. Well, first we'll be adding these two modules onto the same path, and then we'll be performing two things in the center part. One thing is the encryption part and the other thing is the embedding part. Okay, so this is the secret text message which has to be encrypted. Now using this piece of code, we'll simply encrypt it. We'll be choosing the plain text. As I already said, this plain text, it's 16 bytes. This 16 bytes of the plain text will be encrypted using AES algorithm, which has already been implemented, while this 16 bytes of text will be encrypted using the RSA algorithm. And for the same thing, it asks us two values, P and Q. They can be any prime numbers like 53 and 59. Once you have given the two values P and Q, we have generated this encrypted text. If you observe, this is the virtual secret text and this is the encrypted version of the same. We'll be passing this to another piece of code where we'll be embedding this generated ciphertext into a cover image. I will simply run this code and we'll be taking any cover part. It has to be remember that we can input a color image or a black and white image, but regardless of any image, we'll be first converting it to its grayscale model. Let's open this. We'll be first converting it to grayscale model, and then we'll be applying the 3-layer 2-dimensional DWT. And this is the encrypted cover image along with the this is the embedded cover image which has the encrypted text, and this is the histogram for the same. And these are some statistical parameters, the PSNR, the SSIM, the MSI, and the correlation. And at the end of this, we'll be getting an embed image which will be passing on to the receiver side. The receiver side will be first performing the extraction part. We'll simply run this code. And this is the extracted cover. As already said, regardless of the image, which is either it can be color or black grayscale image, we'll be first converting that image to RGB, to grayscale model. That is why when we extract the embedded text, the extracted cover image will be grayscale, because the data, the encrypted ciphertext was embedded onto the grayscale image only. And this is the corresponding histogram of it. And we have this extracted part. If you observe, this ciphertext, which was the encrypted version of the plain text, is same as this extracted part, which has been extracted from the stego image. So the thing which is left is decrypting this extracted text, and for the same we'll be running this piece of code. It applies the inverse AES algorithm for the first 16 bytes and the inverse RS algorithm for the second 16 bytes. The AES is performed according to the code, and for the RSA part we'll be as the PQ values again will be enter the same values which were used to encrypt, 59 and 53. And the encryption and decryption is pretty much faster, and we get the decrypted image. It gets saved as a readable text. If observed, the plain text image and the readable text image, the original secret image, the original secret text and the decrypted text, these are the same, meaning that the proposed system is a lossless system, and the functionality of this module is quite inverse to this module, making these two modules inverse to each other. That is, these two modules are reversible to each other, thereby justifying our project title, Lossless and Reversible Data Hiding using Public Key Cryptography. For public key cryptography, we will be using, we have used the RS algorithm justifying the same. And to add one more step of security, we'll be using the AS algorithm. Thank you.